Normally when we think about light dynamics, we think about something like an optical fiber, about how light flows through a fiber or how light flows through a structure, and we can often even see it with our eyes. But what is really the frontiers of research today is when light is guided on scales that are so small that we cannot really see them with our eyes. And that challenge is something for which the community is developing new tools. We call them near-field optical microscopes. What we have here is in many respects the best near-field optical microscope in the world in being able to see the smallest resolution in space and at the same time also see how light evolves, the dynamics of light itself on femtosecond timescales. And also having the ability to modify and control the frequency of light, the angle and polarizations. So it's a multi-dimensional near-field optical microscopes with record capabilities. Light-matter interactions is an area of research with a lot of important applications. For example, artificial atoms like quantum dots and quantum wells. Today some of them are being used to create the most modern screens. When we look into the implementations of quantum computers, all of them use different kinds of materials interacting with cavities of light. The most important thing about it is that it is a very strong analytical tool. It gives us a new way to look into materials inside electron microscopes and find out new things about them. And what I really hope that we will do with a system like this is collaborate with more groups that have challenges of that type, that need stronger analytical tools, and then find a way to use a system like this to characterize them in new ways. Another kind of application that we're now looking into is actually an idea my students brought up. The question they asked was, can we make a qubit from the quantum electron inside our microscope? And we actually managed to prove theoretically that it is doable. We can make a qubit inside a microscope. The new article that we published in Nature, it's the first time that we can see the coherent interaction of a free electron with a cavity that's holding light. And free electrons have their unique advantages, that they are not fixed in their energy levels, they're not limited in time scales, they're not limited in energy ranges, so we can reach into completely new kinds of light-matter interactions. And that interaction is done here for the first time. I think fundamentally this is the most exciting part of the research. It is the first paper published from our lab, and it's now successful thanks to an amazing effort by the guys in my group. We have really an amazing team here, and it was a challenge that I'm really glad to see is paying off now. There's also a lot of support from the Technion. We are now seeing the first results, but I hope that with new collaborations we'll be able to do much more with other people in Technion and all over Israel.